Hello friends, welcome to EC Academy.
In this lecture, let us understand subband coding. Subband coding is another important imaging technique which is used for multi-resolution analysis. So this is another important imaging technique that is used for multi-resolution analysis of an image. In subband coding, the image is decomposed into set of band-limited components which are known as subbands, and these subbands can be reassembled to reconstruct the original image without any error. So in subband coding, the image is decomposed into set of band-limited components that are known as subbands, and these subbands can be used to reconstruct the original image without any error. This technique is used for speech and image compression, where each subband is generated by bandpass filtering the input image. So the input image is passed through a bandpass filter to generate the subbands of an image. Since the bandwidth of subband is smaller than the original image, the subbands can be downsampled without loss of information. So we can easily downsample the subbands without any loss of information because subbands are having smaller bandwidth compared to the original image. The reconstruction of original image can be done by downsampling, filtering and summing the subbands. So all this process is shown in this figure. This figure shows the principal component of two-band subband coding and decoding system. Here, the input x of n is a one-dimensional band-limited discrete time signal where n can have the value from 0, 1, 2, 3 and so on. The output sequence x cap of n is formed through decomposition of x of n into y naught of n and y1 of n using analysis filters h naught of n and h1 of n and synthesis filters g naught of n and g1 of n. Here filter h naught of n and h1 of n are half-band digital filters whose idealized transform characteristics is shown in this second figure. This figure shows the spectrum splitting properties of filter, where h0 is low pass filter whose output is approximation of x of n and h1 is high pass filter whose output is high frequency. All the filtering is performed in time domain by converting each filter input to an impulse response delta of n. In order to reconstruct the input, we have to select h0 of n and h1 of n along with g0 of n and g1 of n. Here to analyze subband coding, Z transform is used. The Z transform is ideal tool for studying discrete time sampled data system. Now let us consider the Z transform of input sequence x of n, where n is having the value as 0, 1, 2 and so on as x of z. So the Z transform of x of n can be written as x of z, that is equal to summation of n is equal to minus infinity to infinity x of n z to the power of minus n. In time domain, downsampling is done by 2. That's why x down of n can be written as x of 2n. So Z transform of x down of n can be written as x down of z, that can be written as 1 by 2 into x of z to the power of 1 by 2 plus x of minus z to the power of 1 by 2. The upsampling is done by 2 and that can be written as x up of n is equal to x of n by 2 for n value 0, 2, 4 and so on, and it will be 0 for other values of n. So Z transform for this sequence can be written as x up of z is equal to x of z square. Now we can combine equation 2 and 3 and we can write x cap of z, that is Z transform of output, that is equal to 1 by 2 into x of z plus x of minus z. So the system output can be written as x cap of z is equal to 1 by 2 into g naught of z multiplied with h naught of z into x of z plus h naught of minus z into x of minus z plus 1 by 2 g1 of z h1 of z into x of z plus h naught of minus z into x of minus z. Let us consider this as equation number 5. If we rearrange the equation 5, we can write that as x cap of z is equal to 1 by 2 into h naught of z, g naught of z plus h1 of z, g1 of z, that is multiplied with x of z plus 1 by 2 into h naught of minus z, g naught of z plus h1 of minus z, g1 of z, that is multiplied with x of minus z. So this equation is obtained by just rearranging the equation number 5. For error-free reconstruction of input, the condition is that h naught of minus z into g naught of z plus h1 of minus z into g1 of z should be equal to 0, and h naught of z into g naught of z plus h1 of z into g1 of z should be equal to 2. So this is the condition for error-free reconstruction of the input image. Now equation 7 and 8 can be represented in the form of matrix as g naught of z, g1 of z into hm of z is equal to 2, 0. Here hm of z is analysis modulation matrix, which can be given as h naught of z, h naught of minus z, h1 of z, h1 of minus z. If we assume the non-singularity, then we can write the matrix as g naught of z, g1 of z is equal to 2 divided by determinant of hm of z into h1 of minus z minus h naught minus z. Here the analysis and synthesis filter are cross-modulated. For FIR filter, determinant hm is pure delay. That's why we can write determinant of hm of z is equal to alpha z to the power of minus zk plus 1. Here exact form of cross modulation is function of alpha. If alpha is equal to 2, then g naught of n will be equal to minus 1 to the power of n h1 of n, g1 of n will be equal to minus 1 to the power of n h naught of n. If alpha is equal to minus 2, then g naught of n will be equal to minus 1 to the power of n plus 1 h1 of n, and g1 of n will be equal to minus 1 to the power of n h naught of n. Hence, we can say FIR filters are cross-modulated copies of analysis filter with one being sign reversed. So these equations can also be used to show bi-orthogonality of the analysis and synthesis filter. To do this, let us consider P of z to be product of low-pass analysis and synthesis filter transfer function. Then we can write P of z is equal to g naught of z into h naught of z, that is equal to 2 by determinant of hm of z into h naught of z, h1 of z. Similarly, P of minus z is equal to g1 of z, h1 of z, that will be equal to minus 2 divided by determinant of hm of z into h naught of z, h1 of z. Hence we can write g naught of z into h naught of z plus g naught of minus z into h naught of minus z will be equal to 2. If we take inverse z transform, we can write summation of g naught of k into h naught of n minus k plus minus 1 to the power of n summation of g naught of k into h naught of n minus k will be equal to 2 delta of n. So this equation is obtained by taking the inverse z transform of equation number 17. Since odd index terms will cancel out, we can write summation of g naught of k into h naught of 2 n minus k will be equal to g naught of k comma h naught of 2 n minus k will be equal to delta of n. So finally, it can be shown that g1 of k h1 of 2 n minus k will be equal to delta of n. G naught of k h1 of 2 n minus k will be equal to 0. And g1 of k h naught of 2 n minus k will be equal to 0. Generally, we can write hi of 2n minus k, comma gj of k will be equal to delta of I minus j into delta of n. Here I comma j will be equal to 0 comma 1. So filter banks that are satisfying these conditions are known as bi-orthogonal. This below table gives the general solution for the equations which we have discussed. Here in the first column we are having the filters h0 of z, h1 of z, g0 of z and g1 of z. In second column we are having QMF, which is quadrature mirror filtering, and in the third column we are having the equation for CQF, which is conjugate quadrature filter. In the fourth column we are having the equation for orthonormal, which are used for fast Fourier transforms. This block diagram shows the two-dimensional 4-band filter for subband image coding. Here the input image will be two-dimensional, where it will be producing 4 subbands of an image, which is approximation, vertical detail, horizontal detail and diagonal detail. So this image shows the impulse response of 4 8-tap orthonormal filters. This is drawn using the equations which we have already discussed. This is the example of 4-band split of a vase. So here we are getting 4 subbands of an image. The first image shows the approximation, second image is the horizontal detail of the image, third is the diagonal detail and fourth is the vertical detail. This is how an image is divided into subbands. We can use these subbands to reconstruct the original image. This is about subband coding. Hope you have understood the topic. Thank you.